Okay, so chapter 6, we'll do 6.1 today. So for this first one, you don't need to do this. We already talked about this yesterday in class. So you don't need to write this down. I just want to go through this really quickly. Like, don't worry about writing down any of this. You've already gone through this in your notes. But just to show you again, what we talked about yesterday, you can see that, and the tan is what we're talking about here. So you can see up here at the middle part of your table, all the blues, we're ignoring that one. Those follow different rules. So we're looking at just the ones that follow a simple rule. So just the ones in tan. So column 1, I'll have 1 dot, column 2, 2 dots. Now you can also see in here that they don't follow the same ones that I showed you. Most books do show it going from right clockwise to left. I don't know why they have it like that, but you're going to see different books with different rules. But most books that I've seen have what I showed you yesterday in class.
Why are the D rows included in this?
Because they follow different rules. They have a lot more electrons. And so it's not as simple to look at, and they don't follow, they don't have one rule either. They break a lot of the rules. And so it gets really complicated. So in college, if you take college chemistry, you'll learn more about those and what they do, but it just gets too complex to talk about in high school chemistry. So we just don't.
So if we write the dots in a different order, is it technically wrong?
Yeah, because you should learn the order I told you yesterday, because that really is what most books are going to show you. And so it's better to just learn the preferred way to do it.
Wait, I thought it always just went like for 2 of them, it's on each side. I thought it was one on the right and one on the bottom.
Yes, that's correct. So this is not the correct way to write them. I don't know why they wrote like this. Some books do have it different than others, but it's better to just learn what most people do, which is not what you see on here. You can see that on the very right-hand column. Again, I think about this too. Helium only has 2 electrons, and so you just have 2. And normally we show them paired up to show that helium has a complete shell of electrons. The other ones all have 8 electrons in their outer shell. So let's move on to this one. The only thing really to talk about on this slide is what a group is and what a period is. So groups are columns. So this is group 1 right here, group 2, group 3. So all you need to write down on this slide is what a group is. That a group is a column on the periodic table. And it's labeled 1 through 18.
Is this still 5.3?
We're on 6.1 today. And then periods are rows. So a period refers to rows on the periodic table. You have 7 periods or 7 rows. So this is period 4 right here. Period 5. Period 6. Yes. So you should write down in your notes that a period is a row.
5.4.
We're on 6.1 today. Yeah, we're doing a new chapter. So the test will be over 5.3 and then chapter 6. 6 is a very short chapter, so it's not going to be a bigger test than normal because we don't have a lot to cover in 6.
And a group is a column.
Exactly right.
And
Yeah.
there are 18 groups.
Exactly. Yes, there's 18 groups. There's 18 groups and there's 7 periods.
Do you have any tricks for getting pens to write better?
Usually you have to just throw it away. If it's not working, you've tried writing it, then it's probably the ink is probably just bad. If you need a new pen, I have some up here,
No,
but
I have plumbing and just.
yeah, usually the ink just can dry out. It gets cracked or dried, and at that point, just throw it away.
I think he was expecting some like chemistry like equations or like.
Yeah, I mean, sometimes you can add like alcohol or water to it, and sometimes it's usually just not worth it. But sometimes you can, but usually it's just dried out. And it's yeah, be careful. But usually it's just not worth trying to fix. It's better just get a new pen and throw it away. All right. Let's not worry about that one for right now. Okay, so groups are also called families because the elements in one column have similar properties to each other. And so we can think of them as families because they act in a similar way. They're numbered 1 through 18. If they're in the same column, they have similar properties to each other. They act in a similar way. And so for a while, chemists didn't understand this. They didn't really understand why elements in the same column had the same properties. It didn't make sense to them because they're in the same column, but they have different numbers of electrons and different numbers of protons. They weigh different amounts. So how can they behave in a similar way if they have different numbers of protons and electrons? But what they realized over time is that the valence electrons is what really determines the properties of the atom. It determines how they react with other atoms. So if you know the number of valence electrons, you can determine how it will react. And elements in the same column have the same number of valence electrons. And so we know that they're going to behave in a similar way because of that. So because the outer level electrons are what determine the chemical properties of the atom, and because in one column it's the same number of electrons, they will behave in a similar way, and they're in one family. So an example of this would be the halogens. You can see in the bottom picture. You can see helium, neon, argon, krypton, and xenon. Those are the noble gases. They are all in column 18. They all glow under electricity. So if you electrify these gases, they will glow. So that's a similar property that they all have. Now they glow different colors, but they all glow under electricity. And so this gives you neon lights. And so if you want a neon light, you're going to use noble gas. That's what we use in fluorescent light bulbs. We use usually xenon in the fluorescent light bulb. Of course, neon is used in, as well as other noble gases to make different colors.
How do scientists harness the gases? How do you
It depends. Like for helium, for example, you can mine for that. There's big helium mines over in West Texas and Kansas. They're underground. They're locked up underground. So there's a lot of gas locked up below the rock in the ground. You can drill for that. You might have heard of fracking before. Do you know what they do in fracking?
They drill in and then drill sideways.
Good. And what do they bring out?
Oil.
Oil, natural gas. So there's methane or natural gas also locked up below the shale, the rock layer. So we are able to mine for gases also. It sounds strange, but there's a lot of gas, different kinds of gases below our rock layers, which we can get. So that's how you can get helium. Other gases like argon, it's in the atmosphere, and you can just isolate argon. You can use distillation to do that. You can cool down the gases until some liquefy and others don't. And you can then pull out the gas that you want, and you can purify air that way. So a lot of these gases are naturally either in the atmosphere or below the ground. We can get them that way. Helium might eventually run out though. Helium's getting more expensive. You might have noticed that. It's getting more and more expensive because we're getting less and less of it.
How can we get
Yeah.
less and less? Does it burn up?
Yeah, we use it and it dissipates in the atmosphere.
Well, what can you purify it back out of the atmosphere?
It's hard to do when it's just so scattered because most of helium is below ground. Most is not in the atmosphere.
Huh.
And so it dissipates and it's harder to isolate at that point.
Well, once you get enough of it in the atmosphere, won't it be easier?
Well, it might go to space, like a lot of gas does leave.
Oh.
And it just scatters.
So does that mean the mass of the Earth decreases?
Well, we do have some space dust that comes back in. Asteroids hit Earth's atmosphere, space dust and things like that. But we do lose some gas too, but the amount is pretty minimal. We don't have gas not weigh very much to begin with. The amount that we lose is not much, but yeah, I mean, slightly it does vary a little bit. Earth is not a closed system. We do gain some matter from space, and we do lose some matter as gas does move out of our atmosphere. Majority of gas does stay here on Earth's surface, but some gas does leave as well. So everybody have these down? Okay. We mentioned this before, that the proton number gives the element its identity. So if you change the number of protons, you get a different element. So if you take, carbon, for example, carbon has 6 protons, and you add 1 more proton to carbon, it becomes nitrogen. You've changed its identity by adding a proton to it. So in theory, you could take any element, say you could take copper and add some protons to make it turn into gold. That's a possibility. Now, we haven't done that yet, but it's possible in the future that we could do that. So atoms only change the number of protons through nuclear reactions. There's no chemical way to change the number of protons. So by bombarding atoms with protons, sometimes they stick. And in that case, the atoms can sometimes get larger in size, but that's for very, very large atoms. But that's how we make new atoms. You might have heard about man-made atoms. Anything above element number 92 is man-made. And they do that by bombarding elements with protons until they stick to the nucleus and they create a new atom. So far we go up to 118, but we might possibly make more. We just don't know at this point if we can. They're very unstable. The ones in the last column, or the last row right here, are not very stable. They last for a nanosecond, a billionth of a second. And it's hard to keep them together. They're just so big, they fall apart almost instantly.
How do they track whether they actually exist or not?
Yeah, they have traces of them. So what they can do is they can see a trace of it before it dissipates, because they're radioactive. And so you can see traces of that element before it falls apart.
Are there any that actually have a substantial impact on things around them? Are there any so radioactive
Are they so reactive
that they have a substantial impact on objects around them?
Not the man-made ones, no, because again, they don't really last for too long. Now for like uranium, which is naturally occurring, that's radioactive, and it's naturally, you can mine for that one. And so that is more of an impact. But yeah, the ones that are man-made, most not so much. Most fall apart so quickly. But there are some. But most you have to have ones that are naturally occurring to really have much. Americium is an element that we have in smoke detectors, and that one is radioactive and big. That one is somewhat stable. But most of the ones that get above that are just really not very useful. They don't stay intact. This is a picture of an atom smasher. It's underground. It's a couple of miles in length. And so the atoms will just accelerate through this tunnel underground, and they get faster and faster until they're near the speed of light and they collide together.
It's like the Flash. Like, have you seen those?
Oh, really? I've never seen that.
From the one on Netflix, the Flash. They like have to run in this thing so they can like break some state like that. Like it was.
Oh, that's cool.
Anyways, yeah.
How do they accelerate the atoms?
Magnetism.
It's so you can time jump. It's cool.
What is that?
Oh. You can make the atoms charged, because atoms have charges, right?
Yeah.
And magnetic fields affect charges. And so using a magnet, you can affect a charged particle. So the atoms are meant to collide with each other, and it's hard to do. It doesn't happen too often. It's a lot of trial and error. But if they do collide, what can happen is you can have either a new atom where it gets bigger in size, which is the hope, or it can fall apart into smaller atoms. So those are two things that can happen. Now, what they also hope to have happen sometimes is to smash the protons themselves into smaller particles. So they're able to not just create new atoms, but they're also able to smash the protons and neutrons into smaller things. And the idea is to find new particles that make up the protons and neutrons. So far, they found about 30 different particles that are smaller than protons and neutrons. And these are called quarks. So let's look at, so we talked about the groups so far. We're going to do that. Sorry, let me see really fast. Yeah, we'll do that a little bit later. Okay, so we'll talk about the periods now, which are the horizontal rows of the elements. So as we've already talked about, there's basically three distinctions that we can make in the periodic table. You have nonmetals, you have metals, and metalloids, which are in between. So looking at one of the periods that contains beryllium, magnesium, calcium, strontium, and barium, this is period number 2. So these all have similar properties. They contain all metals. So common properties of metals is that they're solid at room temperature. There's only one metal that's not solid at room temperature. Mercury, exactly. So mercury is the only metal that you're going to see liquid at room temperature. Most are shiny. And they conduct electricity and heat very well.
So stones conduct, or most stones conduct heat pretty well?
Stones do, not so much electricity though.
Well, yeah, but if you put them in a fire and think how they conduct heat, what are they made of?
Oh, well, there's a lot of minerals that make them up. So they do have things
they're
like
just
calcium and phosphorus. And so they are made of metals, minerals, but they're not fully made of them. And because they're not fully made of metals, they're not electricity conductive. But they do have a lot of metals generally inside them, things like calcium, phosphorus, potassium. But also nonmetals too, like chlorine and bromine. Everybody have these down?
What does mercury look like when it's solid?
Oh, it would look the same. It's silver. I mean, you can see up here, you probably have all seen this, the mercury up here. So you can see it's silver. And so if it were to solidify, just look the same, it just would be silver. Nonmetals. So things like oxygen, nitrogen, and carbon. Nonmetals are usually gases at room temperature. See, again, like nitrogen, oxygen, carbon are good examples of nonmetals. And the majority of them are gases, like oxygen and nitrogen are gases. Carbon is solid at room temperature. It's a black powder. You can see it in this top picture. It's right here. They don't conduct electricity or heat very well. So they're insulators. The yellow powder is sulfur. And then this is phosphorus. The white sticks are phosphorus. And then that bottom picture is bromine, that orange liquid. So it's really one of the few liquid nonmetals at room temperature.
So oxygen and nitrogen are gases?
So yeah, they are gases, yes. So, yeah, they are. At room temperature, they're gases. But you can cool it down to make them liquids or solids. But at room temperature, yes, they are.
Oh, sorry.
But every element has a solid, liquid, and gas nature. So every element that we've talked about can be solid, liquid, or gas. But at room temperature, they have one state matter, right? At room temperature, all metals are solids. But you can also have liquid metals and gaseous metals. With high temperature, they can become those. But on the periodic table, most nonmetals are going to be gases. So we have these down? Okay, metalloids are in between. They have properties of both metals and nonmetals. Examples would be germanium, which is the top picture right there. That's the silver chunk. Boron, the middle picture has a B in it, and silicon, the bottom picture. So these are used, they're important in electronics. Computers use them. They're semiconductors. They can be conductive at certain times. Other times they're not. So that allows control in the electronics.
Is this what they use for, what's it called, like electric magnets?
Oh,
Where they
electric.
can send electricity through it and it'll become magnetic.
Yeah, I mean, you can just run electricity through a copper wire and you get a magnetic field. So you don't have to have a semiconductor to do that. Anytime you run electricity through a wire, you get magnetism from that. So you can take a nail and just wrap wire around the nail, electrify the wire, and you become magnetic just from that.
If you ran the electricity through it long enough, would the nail become a true magnet?
Well, no, I don't think that would be enough. I think you need another magnet to do that. I haven't tried that, so I'm not for sure, but I don't think so. I think you need to have another magnet to actually align the electrons properly. On the periodic table in the middle, you have transition metals. These are the ones that are pink on here. So the yellow ones are standard metals, things like calcium, potassium, but then in the middle with the pink section, these are different properties from the other metals. So when you think about metals, you think about these ones. It contains things like gold, copper, iron, silver. We don't really think about calcium as a metal, even though it is, or phosphorus, or sorry, not phosphorus, potassium. Because generally we don't see calcium and potassium on their own in nature. We usually see it locked up in salts.
So how are they different than just normal?
So they follow different rules as far as their charges go. They develop different ions. They're also very stable. Standard metals are not very stable on their own. And so they're pretty explosive, actually. Sodium is a standard metal, but you put sodium in water, it explodes immediately. And you get a big fire from it. So transition metals are stable, generally very stable. They don't really react very much. They can get different charges, so they can have different colors to them. So they're very colorful. They're used in gemstones. Those are the big differences between the two of them. Does everybody have these down? We already talked about those top two bullet points, so don't write those down again.
Is that person holding gold or copper?
That's gold.
Uh,
But on this slide, start with the third bullet point and downward. So yeah, the top two pictures are gold. Gold is very malleable. You can hammer gold into a very, very thin sheet. And so gold can be incredibly thin. So you can have gold foil, gold leaves. It's one of the best metals at being made into very thin sheets. And metals as a whole have this property that they are malleable. They're also ductile. You can make them into wires. And so the bottom picture shows you gold, copper, and silver wires.
What's the difference? Like, why could one be one but not the other?
What do you,
Or, sorry, why could something be malleable but not ductile? Because if you can make it really thin, you should be able to make gold.
oh yeah, both would be. Yeah, no, metals have both properties. Now, some are better than others. Like gold is the best at being malleable. But all metals have that same property. They are all malleable to a certain extent and are all ductile. Gold is the best conductor. So it's a preferred conductor in electronics. It's just so expensive that it's only used when you have to use it. So computers and your phones do have some gold in it, just not very much because it's expensive. So copper is a preferred conductor in most wires because it's cheaper than gold and silver. But gold is the best conductor, silver is next, copper is third. Copper also is quite expensive, but not as expensive as silver or gold. But lots of times in an abandoned house, a thief will come in and take the copper wire because it's pretty expensive. That's one thing they're going to look for in houses that are abandoned. And they'll even take copper from the street lights. You know, they'll hitch their car up, they'll take a chain from their truck and attach it to the bottom of the street light. You know, you might notice there's a lock down there in the street light. That's where the wire is. And they'll pull the copper wire out with their truck because they can sell it for money. Copper is not cheap. Atoms of minerals, atoms of metals. Oh, did you know the last page? So gold, you can take a matchbox size of gold and you can hammer it into the size of a tennis court. It would look like gold saran wrap. It'd be transparent, but gold is incredibly thin and still quite rigid.
Can you get it down to like 1 atom, 2 atoms?
It's possible, yeah, if you really are persistent with it. It look like transparent gold saran wrap. You might have seen drinks with gold flakes in it. They can do that and not be too expensive because the amount of gold is so small. It looks like a lot, but it's so thin, it's not very much gold. And so it looks pretty impressive because it looks like it's gold snowflakes in a drink. But the amount of gold is so small, it's not that expensive. But yeah, people will eat gold on food and drink gold. It's really not going to do anything to you at all. Gold's not reactive, and so it's not going to react with your body. It's not going to do anything good or bad to you. But people just do it just for the look of it, but it's not going to help you at all health-wise or hurt you. In New York, they had this $1 million burger where they had truffles, they had gold flakes, they had Wagyu steak. I mean, it's just ridiculous. But, yeah, $1 million. Yeah, that's a good question. Yeah. I would hope that price, you'd hope it'd be good. But yeah, they have Wagyu. Have you heard about Wagyu steak before? You know, where they take these cows, they massage the cows every day, and they give them vodka, and they just,
It
They
tastes
just, I mean, it's really good. I mean, I don't know if it's worth the price, but it does taste pretty good.
How does misogyny a cow help?
Oh, well, that's gonna, because you are eating the muscle, like steaks are from the muscle of the cow. And so if you take care of their muscles, they're gonna be softer.
Oh.
And so it's gonna be softer and more tender steak. If the muscles are relaxed and healthy, you're gonna get better steak. Because you're eating the muscles of the cow.
I wish I was a cow. Get massage, get vodka, and then get a shot. They do, they stick a bolt through your skull. They
Yes, they do.
They
They
put
shoot
you in a
you all
really
through their
compressed
skull.
pen
Yeah, they want
that the cow
I
can't
got
move.
they want to
massage
kill it
cows.
immediately. They're not gonna
Yeah, they
like-
do. I mean, you
Then
gotta
they
kill
get a
them
gun
somehow.
shot.
Kill 'em
You're not
immediately.
gonna cross their animal.
They shoot the cow.
So.
Well, I wish they would do that. Give me vodka and massage.
No,
I
there's no
would love
contamination or poisoning.
They shoot him with a bolt, it doesn't bleed too much.
Yeah, I wouldn't think so, yeah.
Yeah, it's gonna bleed a little bit, but not that much.
Trust me, those places stink. Really.
Yeah, slaughterhouse, yeah, the smell is just awful.
Slaughterhouses.
Yeah, I've heard people thinking about 100 years, we'll look back on the time people ate meat as just the barbarians, that, we'll get to a point in the future when people don't eat animals anymore.
Ew.
Because they will be able to make meat in the laboratory without animals that will
That
taste.
sounds like McDonald's.
That would taste the
Cows
same.
will overrun the world.
So they think in, 100 years, we'll look back on this time as people killing cows and pigs. That's just barbaric
But then
time.
they're gonna be like, well, the cow farts are like, yeah, global warming, so we have to like kill the cows.
I know, they'll talk about that. I know.
Have you heard that they put cows in barns and when they fart, they compress the methane gas into the tank?
I've heard that, yeah. Yeah.
Do you know if it's true or not?
No, it's true. I mean, yeah.
Seriously?
I mean, you can do
I
that.
will build the
Because
biggest
cows
bomb
supposedly
that America
emit
has
so
ever
much
seen.
gas that the gas they emit is they're concerned about global warming contributing to that. So yeah, Alexandria Ocasio-Cortez, a congresswoman, she is really concerned about the cows. And so she doesn't want us to eat beef anymore.
Wait, who is this?
And Alexandria Ocasio-Cortez, also Kamala Harris has talked a lot about this, about how she wants to have hamburgers. So she's even admitted that she likes hamburgers, but she doesn't want us to have them.
Oh my god.
So they're moving that way.
And then they're gonna be like, oh, she's just giving up her kid.
Next they're gonna be like, what?
I know.
People.
People are very stupid.
Unbelievable methods.
But the thing is that, okay, yeah, we know these gases can make the climate warmer, but is it worth making our lives miserable to make 1 degree difference in temperature? That's really the question.
No.
It definitely, methane gas will make the climate a little bit warmer. Carbon dioxide makes the climate a little bit warmer. But if it's 1 degree difference in temperature, is that we're spending trillions of dollars and giving up all the things that make life convenient, like our cars?
And
Hamburgers. People will lose jobs, yeah. Which is their livelihood. Basically, you're destroying people's lives.
Cattle have been around for hundreds of thousands of years.
Right. Yeah, I know. Yeah, that's a good point. I mean,
And
yeah.
And then they're like, we should only
That's
have
why you
electric
said
cars,
cows
like,
just
shouldn't be
yeah.
using your gas cars. I'm like, literally, you have to burn coal to get the electricity.
That people forget about that. You have to
Like-
burn coal. Yeah, electric cars are not good for the environment because you have to burn a lot of coal, and the battery itself has to use things like lithium and acid. And so that's not good for the environment either. It's a lot worse for the environment actually than your oil cars. And so they forget about that too, that these batteries that are producing are pretty toxic to the environment.
You know what, we should put those cows on a diet, hook them up to a carriage, and see how they like it.
Just send the cow.
I mean,
Have you ever seen a skinny cow?
yes, it's so nasty.
it's gross, and they're really not that skinny. They're still fat. They might try gases to cool.
Yeah. All right. All right, so metals, we'll talk about this a little bit and move on. So metals have 1 to 3 electrons in the outer shell. Metals give off electrons very easily. This top picture shows you metallic bonding, what it looks like when atoms bond that are metals. So basically what you have in here, the red and blue dots, that's a nucleus, and the white specks are electrons. And so we don't see the planetary model of the atoms in this situation. We don't see a circular orbit of electrons around one nucleus. We see the electrons scatter throughout the entire metal. So electrons are mobile in metal. They don't stay in one place. That's why they're conductive. Because what's electricity? Electricity is pure electrons in motion. That's what electricity is. So electricity is just electrons moving. And metals also have the same thing. Metals have electrons moving through the wire. So that's why metals are conductive of electricity, because they can move electrons through the wire. And that's what we get as electricity. That's what metallic bonding represents. So we have the nucleus, positively charged nucleus, which is around a sea of electrons. And the white specks are electrons. How do you move the electrons? Like, how do you make them move?
Oh,
How do you make them move? You create voltage. And so what you have to do is create a positive and negative imbalance. You have to have one side positive, one side negative, and that creates electricity, the movement of electrons at that point. Because electrons are negatively charged. Exactly right. Mhm.
Can you also just make an overload of electrons in one certain area and kind of like water they want to get out?
And that makes them negatively charged. So if you have a buildup of electrons, that's a negative charge area.
Oh,
And you have that's what we call its voltage, basically. It's an imbalance of charge. And so you have a negative side, and that negative side then creates a positive side. Basically creates pressure. You can think of voltage as pressure too. You know, you can think of it as buildup of pressure, which they have to move out of that pressure area. So this explains the properties of metals. Again, I talked about conductivity. So they're conductive because electrons can move through the wire. This also explains why you can crush metals, or why you can make them bend, because the atoms are not confined to one place. They can move with the electrons. Atoms and nonmetals have electrons just around their one place. And so they are not very flexible. But metals are very flexible. The atoms are not bound to just one place. So nonmetals break and tear, metals bend, because the atoms can move with the substance. Going on to so we're going to look at the different groups now. We're going to go to group 1. Group 1, this column right here, these are the alkali metals. They're highly reactive. So you can put them in water and they explode. So all the metals can do this in this column. Lithium, sodium. It depends on the metal. Lithium is more of like a bubbling, kind of looks like soda, like Sprite. It's kind of like that, but it's hot bubbles, so it really heats up. But that's mostly what you see is bubbling and some smoke. Sodium is a good explosion. Sodium can look like the top picture with a good amount.
oh my gosh, how much
Can we do a
sodium do you
tiny
have?
one in our classroom, or is it?
Yeah, no, we can. I do have some sodium, and the amount that I have, though, we can't have an explosion in the classroom because that wouldn't be dangerous. But we could have, it's a small fire that you can get in the classroom. You can see a small pop and a small fireball. So basically what you see is a ball of fire that dances around in the water. So, but a larger chunk you do get an explosion. There was one year we had students who did have an explosion of sodium. They put too much in the water and they were really lucky, but they had holes in their t-shirt from the burns. They were, yeah, it The table had burns on it. Molten sodium had basically flung out and gone onto the table onto their shirt, and they're lucky they didn't get it like worse injuries. But so we can't have a big explosion, but we can see a small explosion.
What if we put like a bunch of sodium in one container of water and took it outside?
Yeah, the problem is that we can try that. The problem is the delivery method. See, you have to have a good way to deliver the sodium, which
What if- This sounds really, stupid, like ancient. You tie string or something to a piece of plastic or paper,
yeah,
put sodium on top of it and just pull it off.
that's a good way to do it. I think we could try that. Yeah, that could work.
Big brain.
Something like there's like some good stuff, but like, when are we gonna do the cake section?
So did you want to do that?
I mean, I think that.
Yeah.
Do what?
It's not fun.
Like, do what?
I mean, it just smells so bad.
Yeah, the smell, I mean, it depends on where you get them from. I think the ones I get don't really smell too bad. I don't think the smell, I don't think it's too bad. I mean, some years they were bad, but I think it's gotten better as far as smell goes.
How do you get that?
I order them online.
They filled it in.
All right. So before you leave today, make sure you turn in your homework from last night. If you haven't already, I need your homework 8 and 9.
No, you rig it? No. You rig it?